Okay, this is the review of Unit 8, Momentum and Impulse by Matt Harris and Connor Mulligan.
Alright, so we're going to start off with some basic concepts. First of all, momentum. Now, momentum is always conserved in a closed system. The total momentum before collision is always going to be the same as the total momentum after. Now, here are some important variables for you guys to know. First of all, P is equal to momentum, M is equal to mass, and V is equal to velocity. Now, the important equation for momentum is P equals M times V, and of course we know that means momentum is equal to mass times velocity. Now, for the conservation of momentum, the P initial, so the initial momentum, will always be equal to the final momentum for a closed system.
Okay, basic concepts of momentum continued. The conservation of momentum, which was P initial is equal to P final, represented as an equation looks like this. P1 plus P2 is equal to P1 plus P2. And if we break that down, knowing that momentum is equal to mass times velocity, we have mass 1 times V1 plus mass 2 times V2 is equal to M1 times V1 plus M2 times V2. And this can be used to describe a collision, or the momentum in a collision of objects.
So now we're going to show you a couple problems that have to deal with momentum.
Okay, a closed and an open system. Momentum is only conserved in a closed system. Well, what is a closed system? A closed system, and there is no such thing as a closed system except for the universe, but for our purposes we will consider closed systems as being in a perfect world. A closed system has only inside forces acting upon it. It does not allow things to leave it, so anything in a closed system will remain in the closed system, any object in a closed system. And momentum within a closed system is always conserved. An open system allows outside forces to act upon it. It allows things in and out of the system, and momentum is not conserved in an open system. The same for both systems is forces act upon them.
So how does Newton's second law relate to momentum? Alright, how does an object gain or lose momentum? Momentum changes when an object changes either its mass or its velocity. A change in velocity, or change in v, is an acceleration. Acceleration is equal to the change in velocity divided by the change in time. So let's connect that idea to this idea in Newton's second law. Let's derive F equals m times a, or force is equal to mass times acceleration. So we know that we can break down the change in acceleration as the initial velocity, the final velocity minus the initial velocity, and divide that by time. So now we have F is equal to m times the quantity of v minus u divided by t. So to break that down a little further, we can just distribute out the mass. So we have F is equal to mv minus mu divided by t, which can also be equal to force is equal to the rate of change of momentum, which is just the change of momentum divided by times, because the rate of change of momentum, which would be the change of momentum over the change in time. And that's how we get to F is equal to delta P divided by delta T.
Alright, basic concepts of impulse. Well, impulse is the change in momentum. So some variables that we need to define for impulse are force, which is F, T, time, and delta P, which is equal to momentum. So this means that the equation from the previous slide, F is equal to delta P over delta T, is almost our equation for impulse. If we rearrange that and divide by or multiply by delta T, impulse is equal to force times delta T, or change in P is, or delta P is equal to force times delta T.
Right.
That's our equation for impulse.
Right. And now we're just going to show you guys a couple of basic problems that deal with impulse.
Okay, calculating impulse from a graph. This is like one of the last things that we looked at in Unit 8, and we found out that we can find the impulse by looking at a force versus time graph, and we found out that the impulse is the area under the graph. This makes sense because as we move to the right on the x-axis of time and the force changes, so the area under that graph would be the change in momentum over the change in time, because momentum is a change in, wait, force is a change in momentum. Just explain, I mean.
Right, okay, so the impulse is the area unit of traffic. So if we look at this, we have time on the x-axis here and force on the y-axis, okay? So we're going to be looking at impulse, which is the area underneath that, so that it would be force times time.
Alright.
Thank you for listening to our presentation on Unit 8, which is Momentum and Impulse. We hope you enjoyed and we hope you learned something too today. Alright, so we have a problem for us here that has to deal with conservation of momentum. So we see that we have a bowling ball that is 5 kilograms and it's hitting a stationary bowling pin. So if the ball has an initial velocity of 4 meters a second, what is the 2 kilogram pin's final velocity if the ball slows down to 1 meter per second? Now the first thing we're going to want to do is draw a picture. It's going to make it a lot easier. You always want to DAP. You always want to draw a picture. So here we go. We'll have our bowling ball right here, okay? And we'll have our stationary pin. Let's do some basic images. So here's our ball, and here's our pin. Okay, so the ball is moving towards the right. We'll define that as our positive direction, okay? So it's moving to the right in a positive direction. It has a velocity of 4 meters a second, and a mass of 5 kilograms. Now the bowling pin, we see that from the problem is a stationary bowling pin, so we know it has a velocity of 0 meters a second, and it has a mass of 2 kilograms. Okay. So this is our P initial, per se. So we know that somewhere in between we have a collision, we'll call that pow, and on the other side of that we will then have two objects moving. So we'll have P final, and there we will have a bowling ball that is still moving, but now it has transferred some of its momentum into the pin, so the pin is also moving. Now the problem tells us that the ball has a velocity, a final velocity of 1 meter second, and it has a mass still of 5 kilograms because that hasn't changed. And we also know that the pin still has a mass of 2 kilograms, but the velocity is unknown to us, so we'll put a question mark there. Now going down into the conservation of momentum part, we know that P initial must be equal to P final. So we'll write that down. Okay. Now that we know that the two momentums must add together here to equal the two momentums there. So we'll do the momentum we know is equal to P is equal to M times V, so we can do 4 meters a second times 5 kilograms, that's for the ball, plus 0 meters a second times 2 kilograms, and that's for the pin. And that is equal to 1 meter a second times 5 kilograms for the pin and the end, so for the final velocity and mass of the pin, plus, of the ball, my bad. And we know that the pin is a question mark, so it has a velocity of v meters a second times its mass of 2 kilograms. So we can solve. We know that this will be 20 kilogram meters a second plus 0 kilogram meters a second, and that must be equal to 5 kilogram meters a second plus 2 velocity kilogram meters a second. Okay. And here we can subtract this over, so we get 15 kilogram meters a second is going to be equal to 2 times the velocity kilogram meters a second. Now in this scenario we can divide each side by 2 kilogram meters a second. and we will come up with a velocity of 7.5 meters a second. And that is the answer.
Alright, we have a fairly simple impulse problem. It reads, a fullback of mass 120 kilograms traveling at 20 meters per second collides with another player and stops in 1.5 seconds. What is the force of impact? So, define our goal, F, and we know that force is equal to delta P over delta T. Well, we know our time, so delta T is equal to 1.5 seconds, but now we have to find our delta P. Well, we know that delta P is equal to P final minus delta P is equal to P final minus P initial. Okay, so our P initial, we know that momentum is equal to P is equal to M times V. So our initial momentum is going to be P is equal to 120 kilograms times 20 meters per second is equal to 2400. That's our initial momentum. Well, we know our final momentum because he stops, so that means I put PI right there for P initial. Our final momentum, as the player comes to a stop, means that PF must equal 0. So delta P, or the change in momentum, is equal to negative 2400. Well, now that we have delta P here, and we know delta T here, we can plug these into the equation. F is equal to delta P over delta T. So the force of impact, F, is equal to negative 2400 over 1.5, and this is equal to, F is equal to negative 1600 newtons. And that's our answer. Force of impact is negative 1600 newtons. Right there. Alright, so we only had 2 problems in our video, so I'm just going to go quickly through the review that was at the end of the Unit 8 packet, and give you guys 4 more quick problems that deal with some basic concepts of momentum and impulse. So number 2, we're going to start off with that one. It says, a constant force is applied to a ball of mass m. The velocity of the ball changes from v1 to v2. The impulse received by the ball is, and the correct answer is B, m times v2 minus v1. And this is true because if we know the impulse is equal to the final momentum minus the initial momentum of the object, and we know that momentum is equal to m times v, so we know that the impulse, change in momentum, is equal to m times v2 minus m times v1. And because m is a constant value here, we can just simplify that out to be the change in momentum is equal to m times v2 minus v1. And that's why number 2 is B. Alright. Next we're going to look at number 4. This is a fairly simple one as well. A ball of mass 2 kilograms falls vertically and hits the ground with a speed of 7.0 meters per second. It's shown in the picture. So first we're going to want to define our traveling downwards as positive and traveling upwards as negative. And again, we know that the impulse, or the magnitude of change in momentum, is equal to the final momentum minus the initial momentum. So we're just going to solve for those values. Our initial momentum is 2 kilograms times 7 meters per second. That gives us 14. And our final momentum is 2 kilograms times, because we're going upwards negative 3 meters per second. So this gives us our P final of negative 6 minus P initial 14 is equal to negative 20 Newton seconds, and that's why D of negative 20 Newton seconds is correct. Next we're going to look at number 9. A rubber ball traveling in a horizontal direction strikes a vertical wall. It rebounds at right angles to the wall. The graph below illustrates the variation of the ball's momentum, P with time t, when the ball is in contact with the wall. Which of the following statements is true? Well, here I circled when the ball is in contact with the wall. So this is a pretty short period of time, but we know that the ball has a high momentum going into the wall, so the y-intercept is a higher momentum, and as it hits the wall, the momentum slows down over time, and the ball accelerates backwards in the left direction, so the momentum just continues to grow, but in a negative direction, because we're going to define right as being positive and left as being negative. And which of the following statements is true? Well, the gradient slope is equal to the force exerted by the ball on the wall, or by the wall on the ball. This makes sense because the ball's momentum went from high to now it's the same but in the negative direction as it hits the wall and bounces off. Alright, finally we're going to look at question 10, which says the ball is held at rest at point X and then released. It drops onto a flat horizontal surface and rebounds to a maximum height at point Y. Well, here's a little picture here where we have to flip the page. Now the question says, which one of the following graphs best shows the variation t with time of the momentum of the ball? So a momentum versus time graph. So here's the picture. Ball goes down and then rebounds up. We say down is positive, up is negative. Well, this previous one was dealing when the ball was in contact with the wall. Well, this is dealing with the entirety of the movement of the ball as when it's dropped and then it goes back up. So, the momentum of the ball, the answer here would be A. So the ball has momentum, hits the wall, we're going to say that's negligible time, and rebounds off the wall with a negative momentum, which means it's changed direction. And that's why A is the correct answer.